Hey guys, today I'm going to present a solution to IMO Short List 2019 problem A4. Firstly, we'll have a look at the statement. We consider real numbers a1 up to an with sum 0. Furthermore, construct a set A of ordered indices I is less than j such that the absolute value of ai minus aj is greater than or equal to 1. Furthermore, we assume that this set A is non-empty. Then we shall prove that the sum of ai, aj over all I, j and a is less than 0. We note that the term we are interested in looks kind of similar to the value of a1 plus a2 plus up to plus an all squared. The only difference is that we are leaving out those products ai, aj where ai and aj are close to each other. And furthermore, of course, we have to divide by 2 afterwards because those are ordered pairs. We see that we can compute the value of a1 plus up to an all squared because this is nothing but 0. Furthermore, as I've just said, this is equal to the sum of 1 is less than or equal to I and j, which are also less than or equal to n, of ai, aj. And this is equal to the sum of I, j in ai, aj times 2, because here we have order, and then we have to add all of those terms that are left out in this sum. So we also must add the sum of I and j between 1 and n, where the absolute value of ai minus aj is less than 1 of ai, aj. So because all of this equals to 0, we only need to show that this sum is positive. So we note this down and we see that it is enough to show that the sum of I and j between 1 and n, where the absolute value of ai minus aj is less than 1 of ai, aj is positive. Taking a look at this sum, we note that any ai of absolute value at least 1 cannot contribute negatively to this sum. This can be seen by the fact that if we consider any aj such that this condition holds, we immediately conclude by the triangle inequality that ai and aj must be of equal sign, or in other words, ai times aj must be positive. So without loss of generality, we could basically assume that the ai lie in the open interval from -1 to 1, because that certainly will not increase the value of this sum. So to do that, we define an index set I of indices small I between 1 and n such that the absolute value of ai is less than 1. So what I've just said translates to this sum is greater than or equal to the sum of all of the I, j in our new index set, where the absolute value of ai minus aj is less than 1 of ai, aj. Originally, it made sense to, instead of taking a look of I, j and a, consider those indices I and j where I and aj are really close together. Because intuitively, this claim makes kind of sense. We are hoping that the product of those ai, aj is positive, which is kind of clear because the only way for such a summand to have negative value is for ai and aj to be really small in absolute value. We use this reformulation to reduce the ai's in consideration to those of small absolute value. Now, at this point, it makes sense to translate our point of view back to where we are considering those ai's and aj's that are far apart, because all of those ai, aj's must have a negative product, which is exactly in the direction that we in the end want to prove. So we can rewrite this sum again as the sum of I and I, ai squared, minus the sum of indices I, j in I, such that the absolute value ai minus aj is greater than or equal to 1 of ai, aj. We have chosen the steps that we did carefully so that the signs of inequality will be correct, and indeed we see that for ai and aj of absolute value less than 1 and their difference being of absolute value at least 1, the product AI times AJ is of course less than 0. Furthermore, that is a square, so it is at least 0. Hence, we can conclude that this entire sum on the left is greater than or equal to 0, which is almost what we wanted to prove. We have now proven that the product AIAJ of I, j and A is less than or equal to 0. Lastly, we rule out the equality case. For equality to happen, we must have equality here and at this point. Our definition of this set AI was a slick way for saying that vlog, the absolute values of those AI, shall be less than 1. But the reason why we formulated this in that way is that we can say for equality to hold here, I must indeed contain all of the indices, because omitting any AI of absolute value at least 1 decreases the size of that sum right here, because any such AI will actually contribute positively, at least by AI squared, to that sum. So for equality right here, we must have I equal to 1, 2, up to n. But this also means that at this point, we are not omitting any of the summands where AI minus AJ is at least 1. But we are given that the set A, which is exactly that, up to order, is not empty. Therefore, we have at least one summand here in that case, which tells us that we can't have equality here. This is because each of those summands are strictly less than 0. So in any case, we have shown that this sum is less than or equal to 0 and that equality cannot hold.